So the two topic that we will cover today is the first one is higher order differential equation, and probably now you know that once you have a capacitor and an inductor in a circuit, you cannot represent that by a first order differential equation. You have to have a second order differential equations, and we have shown this before when we talked about differential equations, and we talked about storage elements in engineering, generally speaking. And with our in our context here as electrical engineer, inductors and capacitors would be the two storage elements. And we say if we have two storage elements, then we have to have a second order differential equation. So how to deal with a higher order differential equation? We'll talk about only second order. We'll not cover anything higher than the second order differential equation. So as we know that so far we only dealt with initial conditions problem, and this one will also be an initial condition. So it's a higher order differential equation. However, we still have it as an initial condition problem. So now here, as you can see, that we will write the function in that format. Okay, so here we will have second order differential equation. I think this has to be dy by dx squared. This is to be the opposite, the other way around. Okay, so we follow the following procedure. Okay, so the procedure here is based on one important thing, that we reduce the second order differential equation to first order differential equation. Oh, there is something problem here. Just take this out, bring it back. Okay. So we first reduce the equation to a second order differential equation. So how we do that? Okay. So we assume that y prime or dy by dx is equal to u. So we introduce the term u. Okay. So now this will be my first differential equation. This is my equation number one. And then this, what used to be the second derivative of my equation, now instead of having as a second order, now we have a first order in terms of u. So now I have y prime or dy by dx and du by dx, and now the function in terms of x and y, and instead of y prime, it becomes only u. So now I have reduced the equation, the second order differential equation, into two first order differential equation. If you go back to the introduction, we said actually this is how we get the second order differential equation from the first place, that we have two first order differential equation. We combine them together to get the one equation second order. Now we are going back. So now we are splitting the second order differential equation into two first order differential equations. Once we do this, then we can apply any of the methods to solve, for example, the Euler methods, modified Euler method, etc. And here is the solution. Sorry. So this is the differential equation that we are solving. This is your f. Okay. So now yn plus 1 equal to yn plus hun. So I'm using the Euler method here. And now, and then un plus 1, which is this one, is u of n plus hf. Now, your function is a function of x, y, and u. As simple as that. So, to show this, let's have an example. So here, this is my second order differential equation. Okay, and I have two initial conditions. Now, for a second order differential equation, you need two initial conditions, but both defined at the same x0, which is 0 here. So we have y at 0 equal to 1, y prime at 0 is equal to 2. We want to use the Euler method to calculate the approximate value of y at point 2 using h.1. So we'll start with h.1 and then, y at point 1 and then y at point 2. So we increase a step of point 1. So when you look here, if you put the equation in this format, So the second derivative of y with respect to dx squared is equal to minus x dy by dx minus y. So this is the function that I told you in terms of x, y, and y prime. Now I want to change this into something else, in two equations. Each one is first order, okay? And we will see now how we will do this, okay? So we'll start from where I stopped. So we have here the second derivative of y dx squared is equal to minus x dy by dx minus y. Okay, I have y at 0 equal to 1 and y prime at 0 is equal to 2. Now I will define dy by dx as u. So this means that the second derivative of y is equal to y prime, or du by dx. It's the same thing. Okay? So then, this will be my first equation. Dy by dx is equal to u. My second equation is d squared y by dx is equal to u prime, which is du by dx, is equal to what? Is equal to this, which is minus x. Now I don't have dy by dx because this is now u. So minus x of u minus y. And this is the function that I told you is now in terms of x, y, and u. So now I have this equation and I have this equation. So I have two first order differential equations. And now the solution to this, yn plus 1 is equal to yn plus h u of n. And the solution to this, u of n plus 1 is equal to u of n plus h function of xn, yn, and u of n. So we'll solve these two equations together. So we'll start with y1 is equal to what? Equal to y0 plus h and u of 0. Okay. So what is y0? I'm not muted. Can you guys hear me or you cannot hear me? Hello? Please, can someone said that they cannot hear me. Yeah, everyone says they can hear me, so it seems that you have a problem in your system. Okay. So everyone said they can hear me. Okay, so it seems that you have a problem in your system, in your audio system. Okay, so y1 is equal to y0 plus h u of 0. Okay, excellent. So let's now substitute. Now y1 is y at point 1. Because we have y defined at 0, I want to have y at point 2 at h equal to point 1. So we start with h point 1. This is equal to y at 0 plus h u at 0. So y at point 1 will equal to, what is y0 is equal to 1 plus what is h is equal to point 1. What is u of 0? U of 0, we know that u is dy by dx. So u of 0 is nothing but dy by dx at 0, or y prime at 0, which is equal to 2. So this is equal to 1.1. Now I have to find u at point 1, which is equal to u at 0 plus h, which is 0.1. Now what is my function? This is my function. So this will become equal to minus x of 0 times u of 0 minus y of 0. Okay, what is u of 0? u of 0 is y prime of 0, which is equal to 2, plus 0.1 times minus x of 0. X of 0 is 0. This is x of 0. This is your x of 0. So this becomes 0 times u of 0, which is 2, minus y of 0, which is 1. So if you do this, this is equal to 1.9. So I know now y at 0.1 and u at 0.1. Excellent. But I want to find y at 0.2. Now, what is y2 equal to? Y1 plus h u1. Now I know y1 and I know u1 from which is, this is basically y at 0.2 equal to y at 0.1 plus h u at 0.1. Okay, so this is y at 0.2 is equal to 1.2 plus 0.1 times 1.9, and this is equal to 1.39. So if the objective is to find only y at 0.2, I'm done. I finished. If the objective is to find y prime at 0.2, sometimes we want to find the derivative of the function, not just the function. We just continue. We'll find y2, which is equal to u of 1 plus h minus x1 u1 minus u of 1. So u at 0.2 equal to u at 0.1 plus h minus x at 0.1 times u at 0.1 minus y at 0.1. We have all the values. So if you substitute this equal to 1.761. But what is this? This is nothing but y prime at 0.2. So I know y at 0.2 and yes, x. Yeah, thank you very much. What is x at 0.1? Actually, it is 0.1 because this is the increment that we have. This is the x. So remember, what is h? So we go from x0 to x1 to x2, etc. Now, what is the difference here is h. So when you start with 0, then this becomes 0.1, then it becomes 0.2. So this is the index, if you may say. Okay, so this is how we deal with multiple or higher order differential equation. So you just need to have this into convert a higher order single differential equation to a lower order multiple first order differential equation. And I said we will just, if I ask you in the exam, it will be only second order differential equation. The final topic that we'll cover in this course is the finite difference method. This is a very powerful method, and we use it a lot to calculate the, in our context, the electric field, the voltage in space. If you know the boundary, if you know the voltage between two different points, and you want to know the voltage or the electric field or magnetic field in between at different x or y coordinates, then finite difference is one of the methods. There are some other methods like the finite element, etc. And this is like a topic by itself, which is dealing with partial differential equations. Now, what is the difference between differential equation and partial differential equation? We mentioned that before. In differential equation, you have only one independent variable. But in partial differential equations, you have multiple. Could be 2, could be 3. 2 if you're working in a space, 2 dimension. 3 if you work in a 3D or in a volume. Okay. So here, since this course only limited to ordinary differential equation, we will limit the independent variable to only one dimensional, meaning I will be going only in the x-axis. Nothing will be going in the y-axis. But I just wanted to draw your attention that this method is very powerful, and what we are covering here is just a touch of it. but it is used widely to solve differential equations, partial differential equations in 2-dimension and 3-dimension space. So let's see here, having a look, trying to understand what do we mean by finite difference method or boundary value problem. As I said, this is just one tool or one method to use the boundary value problem. Boundary value problem is an approach how to solve differential equations. In the previous one, we have initial value problem. So the variable that you want to find is defined at the initial conditions. So usually it is a function of time. When it's an initial condition, so it's a function of time. You know, I'm talking about our context as electrical and computer engineers. I have a capacitor, I have an inductor, I know its initial condition. After certain time, I want to find the voltage and the current in the inductor or the capacitor. Here is different. Here, I know the values at 2 different points in space. Usually, the application for this in space. So when you look here, this is the x-axis and this is the y-axis. We're only interested in the x direction. My variable does not go in the xy plane, but rather only in the x direction. So I go from x0 to x1, x2, x3, and x4. The h here is 0.25, the difference between one x to the other. And I know the value of the function x defined at 0 and at 1, which is the boundaries. Okay, but I don't know what is the value in the middle at 3 different spots. So how to find this? So as you can see here, we are talking here at time is not a function here. We don't talk about time here. We talk about only on space. Okay. Although the differential equation that we'll be solving looks very generic, but I'm trying to highlight where do we see this as electrical engineers. So how we do this? So we convert this one into the basics of the definition of derivatives. If you recall, from the derivative part, we said that dy by dx, one of the approximation is f of x plus of h minus f of x over h, or this is nothing but y at I plus 1 minus yi over h if you use the forward divided difference. And we also defined the second derivative to be equal to this, f of x plus h minus f of x plus f of x minus h over h squared, or we can have it in terms of the y. So we will take the equation, and it's second order differential equation, and we convert it into difference equations like this one. And then we will end up having an n number of equations. We will solve these equations, but they are now nothing but linear algebraic equations. So we use Gauss elimination or any of the methods that we know to solve linear equations. So let's have this example, the same one that I just showed you, and let's try to find the y at x1, x2, x3. So these are the unknowns. Okay, so I need to find y1, y2, and y3. So there are 1, 2, 3 unknowns that I don't know the values, and I know the boundaries only, y0 and y4. So to find 3 unknowns, as we know, we need to have 3 equations. So we'll see how we will find our equations. Okay, now this is the second order differential equation I am interested to solve, which is dy by dx squared plus 2 dy by d of x plus y equal to x squared. So this is my differential equation that I am interested. So as I said, we need to convert this differential equation into difference equations, not differential equations, using the approximation of the derivative and the second derivative we learn in the derivative lesson, and we move on. Okay, so let's see. Our dy by d of x equal to y I plus 1 minus y of I divided by h. Okay, and we have d by dx square equal to yi plus 1 minus 2yi plus yi minus 1 divided by h square. Okay. Okay, let's now write down the equation here. So we'll have this yi plus 1 minus 2yi plus yi minus 1 divided by h square plus 2 yi minus plus 1 minus yi divided by h plus yi equal to x of I squared. So this is the equation now that we will have. Okay. Yes, you are right. We have here a bracket. Okay, excellent. So now I didn't do anything. I just, by the way, there is a typo. I will fix it in the notes. It shows that there is a 2 here. There is no 2 here. I will remove it from the notes. Okay. So this is the what I did. I just substitute the value. That's something we already know. Nothing new here. This is we know from the derivative. I just come to here and I substitute. So I removed the second derivative with this, the first derivative with this, and that's it. Okay. Oh, so this is the 2h that I'm saying. I am telling you that this is wrong. Okay, but later on I managed to remove it. Okay. So now h is 0.25. H is the distance between one x to the other. So it's 0.25. So I will rewrite the equations now. Y I plus 1 minus 2yi plus yi minus 1 divided by 0.25 square plus 2 yi plus 1 minus yi divided by 0.25 plus yi equal to x of I square. So far, so good. So this is will be 16 times yi plus 1 minus 2yi plus yi minus 1 plus 8 times yi plus 1 minus y of I plus y of I equal to x of I square. Okay, now we will collect terms yi plus 1, yi and yi minus 1. So we will have this nice equation, 24 y of I plus 1 minus 39 y of I plus 16 y of I minus 1 equal to x of I square. So this now becomes our equation. Now we have 3 conditions, x1, x2, and x3, or I1, 2, and 3. So at I equal to 1, we will have 24 yi, which is 2, minus 39 y1 plus 16 y0 x equal to x1 square. Okay, now y2 is unknown, y1 is also unknown to me, but y0 I know it. Y0 from the previous y0 is 0.2. So this is one of the initial boundary conditions. Okay, so now I will rewrite this equation as such. So this becomes 24 y2 minus 39 y1 plus 16 times y at 0, which is 0.2, plus what is x1? X1 defined as 0.25. It's a given value to me. This is equal to 0.25 square. This will ask me the question, what is x1? X1 is, we know the value of the interval. I mean, we are going from 0 to 0.25, 0.5, 0.75, and 1. We only know the function y at 0, at 1. We don't know y at 0.25, 0.5, and 0.75. So the x's, x1 is 0.25, x2 is 0.5, and x3 is 0.75. So now this equation becomes, if we collect terms, 24y2 minus 39y1 equal to minus 3.1375, and this is my first linear equation. So now I will have here a linear equation and move on. Now let's find the second linear equation. So this is when I equal to, remember, I equal to 1, 2, and 3. If they have any questions here. Okay, we know x1. Yes, we know x1. Okay, let's move on. So here, if I use I equal to 2, now I will go back here and I will substitute here in this equation. Y equal to 2, this becomes 2 plus 1, 2, 2 minus 1, and so on and so forth. Okay, so this becomes 20. Now I'm just collecting terms right away. So it becomes 24y3 minus 39y2 plus 16y1 equal to x2 squared. Now I don't know any of those values. I don't know y1, y2, or y3, but I only know x2 squared, which is x2 is 0.5, so this becomes 0.5 squared or equal to 0.25. So now I have my second equation. Then I will have I equal to 3, same thing, I equal to 3, so I will substitute here. This becomes 3 plus 1, 3 minus 1, and this becomes x3 squared. So if this is the case, this becomes 24 y to the 4 minus 39y3 plus 16y2 equal to x3 squared. Now y4, I know it. y4 is 0.8. This is one of the boundary. This is the other extreme boundary condition. So this becomes 24 times 0.8 minus 39y3 plus 16y squared equal to x3, which we know it also, 0.75 squared. Okay. Now we will have 3 equations, linear equations in terms of y1, y2, and y3, which is our unknowns. So this becomes minus 39, 24, and 0, 16, minus 39, 20, 24, 0, 16, minus 39, and this is equal to minus 3.1375.25 and minus 18.6375. So now I have this set of equations. I will solve for y1, y2, and y3, and this is the answer.